Send them in this. You send them forwards. Oh, you send the details. So those who are online, am I audible? Yes, sir. Yes. So what was the last topic we discussed? So last topic, what I remember is Rutherford's drawbacks, right? So drawbacks of the Rutherford experiment, is that right?
Sir, your voice is very low, sir.
Voice is very low. I'm very close to the computer. Huh? Let me check it. Now is so I think all my devices are connected properly. Is it fine now?
Better, sir.
Better. Huh? Is it the case with everyone? No, sir. You're able to hear me clearly? Yes, sir. Okay. There it is 940. Okay. That's it. So, to what I remember, last concept that we discussed was Rutherford's drawbacks. Is that right? So now we'll go to the next model of atom that is called as Bohr's model of atom. Before we see Bohr's model of atom, first let's see a condition called as Bohr's quantization condition, which we have already discussed in the previous chapter. Right? So we have seen that in the previous chapter. What was it? Right. So here, if you see, if we consider an electron, right? If we consider the motion of an electron in a circular orbit of radius r around the nucleus of the atom, then according to de Broglie's hypothesis, this electron is associated with wave character. Accepted? Meaning, if I take a circular orbit like this, so if I take a circular orbit like this, an electron revolving the circular orbit is going to get associated with the wave-like structure in such a way that if I take this to be the wavelength, then what does the condition tell you? If I take the orbit's radius to be r, then the circumference should be equal to n times each wavelength, where small n stands for integer value. Yes or no? So this we saw in the dual nature of matter itself. So it is n time lambda. So 2 pi r will be equal to n time lambda, which implies lambda, or wait, 2 pi r is equal to n times lambda. Now what I do is, 2 pi r will be equal to lambda is h divided by mv. Am I right? So it is going to be h divided by mv, which implies h is equal to, or h by 2 pi is equal to mvr, and you have an n also. Am I clear, guys? Are you able to understand what I have written? Yes or no? Right. Now this m into v into r is called as angular momentum. And this angular momentum L is equal to nh by 2 pi is what is called as Bohr's quantization condition. This is what is called as Bohr's quantization condition. Okay. So the Bohr's quantization condition says that the angular momentum, this is the statement, angular momentum is equal to integral multiple of h divided by 2 pi. So angular momentum is an integral multiple of h divided by 2 pi. Are you able to understand? Shall I proceed? Right. So have this in your mind. So I'll tell you something. Based on the mistake made by the previous scientist, the next scientist would have proposed the next postulate. Right. So the next concept that we are going to see is Bohr's atomic model postulates. You know what are postulates, right? Have you heard this word? Where? I've already told you. Yeah. Okay. So what are postulates? Postulates are basically axioms without proof. Axioms where it is considered to be a true statement. Right. So you would have learned it in Euclid's geometry in your 9th standard. So what did Rutherford say is, he told that if I have an electron, the electron revolves in a circular orbit. So what did he say? He told that the electron revolves in a circular orbit. But the mistake that he made is, electrons revolve in circular orbit, no doubt, but they cannot revolve in random circular orbit because they start losing energy. Okay. So Bohr made a correction here. So electrons cannot revolve in random orbits. Rather, they would revolve in those orbits which are called as stationary orbits. Right. So he told, while the electron is revolving in some permissible orbits, an electron does not radiate energy. These non-radiating orbits are what are called as stationary orbits. Okay. That is the first point to be noted. Second is, he explained about the condition called as frequency condition. So frequency is basically related to energy. So here the frequency condition is stated like this. If you take an atom basically can emit or absorb radiation. What will it do? It can either emit or absorb radiation. In what form? In the form of discrete energy photons. And when will this happen? When there is a transition of electron taking place from higher to lower orbit or lower to higher orbit. Okay. So if I take E1 and E2 to be the energies associated with the permitted orbits, then the frequency of the emitted or absorbed radiation is given by h nu is equal to E2 minus E1. So make a note of this. So E2 minus E1 is equal to h nu is what is called as Bohr's frequency condition. Are you able to understand? Yes or no?
Sir,
Tell me that.
sir, can it be negative when E2 is greater than E1?
Generally, it will not be like that. Energy of the higher orbit will be more. Why is it so? We'll see. You will understand it after I derive certain things. Okay.
Okay.
Am I clear with this? Okay. So now make a note of the following points. So what are the two quantization conditions we have seen? So what are the two conditions we have seen? First is L is equal to NH pi, or L is equal to MBR is equal to NH divided by 2 pi. This is called as Bohr's quantization condition. And the second that we saw is E2 minus E1 will be equal to h nu. And what is this called as? Bohr's frequency condition. Right. So having these 2 points in mind, we are going to derive the radius of the nth orbit in which the electron is going to revolve. Okay. So the heading is going to be radius of nth orbit. Okay. If I have an electron which is revolving in the nth orbit and I call the radius of the nth orbit as Rn, for instance. Are you able to understand? Right? Now our job is to derive what is going to be the radius of this circular orbit. Remember, here you have the nucleus. So nucleus has a charge of Z into E, where Z is atomic number. So Z times E, and you have an electron which is revolving in the circular orbit. Right? So what is the force between electron and nucleus? It is obviously the electrostatic force. So it is obviously the electrostatic force. And how is electrostatic force given as? K times ZE square divided by Rn square is equal to, okay, let me call this as 1. But here what I'm saying is the electrostatic force provides the necessary, see, for any object to be in a circular part, what is the necessary force called as?
Centripetal.
Yes, it provides the necessary centripetal force. So what I will write is Kz E square divided by Rn square is equal to mv square divided by Rn. So what we get cancelled? Rn and 1 Rn is gone, which implies Kz E square divided by Rn is equal to m into v square. Now how to proceed from here? Now how to proceed from here? So, for example, if I write Rn is equal to Kz E square divided by mv square, that will be the final answer. But remember, I should not write this answer. Why? I should not leave the expression like this. Because Whenever you try to derive any formula theoretically, so whenever you are deriving any formula theoretically, what should happen is you need to ensure that all the quantities involved in the known expression should be in a way that you can calculate it. For example, K it is the constant. Z is atomic number. You can get it from the periodic table. E is the charge of electron. You can take it, you know it already. M is the mass of the electron. But what is V? V is the speed of the electron in the orbit. Nobody has seen the atom. Then how are you going to calculate the speed? So we need to eliminate it. So for that to get eliminated, what we will do is we will use the Bohr's quantization condition. So from Bohr's quantization condition, what can I say? MVR is equal to NH divided by 2 pi, which implies V is equal to NH divided by 2 pi into M into R. This is true. Okay, make a note of this. Over. So what I'm going to do is I will use 2 in 1. So when I use 2 in 1, I get Rn is equal to K Z E square divided by M into V square. So what is V square? That is N square H square divided by 4 pi square M Rn square. M square no. Why did I get everything as a square? Because this NH by 2 pi, I have to square this and substitute it in this place. Right? When I do this, we get Rn is equal to, so M will get cancelled, Kz E square divided by N square H square divided by 4 pi square M Rn square. So this whole thing will go to the numerator. So Rn will be equal to Kz E square divided by N square H square into 4 pi square M Rn square. So one Rn is gone, which implies Rn will be equal to N square H square divided by K times Z E square into 4 pi square M. Is it clear? So Rn will be equal to N square H square divided by K. I can write it as 1 divided by 4 pi epsilon naught into Z E square into 4 pi square M. So 4 and 4 are gone, pi and pi are gone, which implies Rn will be equal to N square H square epsilon naught divided by M Z E square into pi. Those who are online are able to understand.
Yes, sir. Yes, sir.
It's an important derivation. Okay, make a note of it. Seriya? Now see, if you look at this expression, can you tell me what are all the constants? H square is a constant, epsilon naught is a constant, M is a constant, Z E square pi is a constant. Right? So actually Z is not a constant, you can find it out. So there are two things that will vary in the expression. One is N square and one is Z. So when you substitute all the known quantities, you will get Rn is equal to 0.53 into N square divided by Z angstrom. Okay, to 0.53 into N square divided by Z angstrom means instead of remembering this whole expression, you can remember this one to solve it. So based on the orbit number and the atom you're dealing with, you can substitute the value of N and Z in it. That's it. Am I clear with this? So, if I put n is equal to 1 and z is equal to 1, what happens? What atom is it? It is a hydrogen atom. So, I'll get R is equal to 0.53 angstrom, and this is what is called as Bohr's radius. Here, I think you would have seen this expression in your chemistry and atomic structure. Does anyone remember this? It is a part of atomic structure from your 11th standard. Only thing is you will not have this derivation at all. Clear? Shall I proceed? Yeah. So, yeah. I don't have that number because I have to log in. Yeah. You have Sumit's number. Okay, just drop if there is any. I will give you. I'll send it. Okay. So I hope the derivation was easy, right? Now, the next question is, energy of an electron in nth orbit. So energy of an electron in nth orbit. So if I take this to be the electron, then what is going to be the energy of it? Right? How to calculate? So when I take the total energy of electron, then it is the sum of kinetic energy of the electron plus electrostatic potential energy of the electron. Why did I use the word electrostatic? Because it is because of electrostatic force only it is able to be in the circular path. Am I right? So what is going to be the kinetic energy? It is going to be half mv square plus the potential energy is k into Ze into minus E divided by Rn. Here. So it is k Ze into minus E divided by Rn. So from this I'll get half mv square minus kz E square divided by Rn as the total energy. Now keeping this in mind, now see, using Bohr's, using Coulomb's law, what will I get? So using Coulomb's law, we will get mv square divided by Rn is equal to kz E square divided by Rn square. Here. So Rn and Rn will get cancelled, which implies mv square is equal to kz E square divided by Rn. Let this be 2. Is there any doubt till this step? Clear, no? So using 2 in 1, what are we going to get? So in the place of half mv square, I'll replace it with kz E square divided by Rn. So kz e square divided by 2 times Rn minus kz e square divided by Rn is equal to minus kz e square divided by 2 times Rn. That is going to be the answer. Okay. This is going to be the energy of the electron in the nth orbit. What is it? It is the energy of electron in nth orbit. Okay. Now comes an important question. En is equal to, I'm writing it again, minus kz e square divided by Rn multiplied with 2. Now the point is, what is the value of Rn? Rn is n square h square epsilon naught divided by pi m z e square. So Rn is n square h square epsilon naught divided by pi m z e square. So if I take this value and substitute it here, then En will be equal to minus kz e square divided by 2 into Rn is n square h square epsilon naught divided by pi m z e square. So this will be equal to minus 1 divided by 4 pi epsilon naught into z e square divided by 2 into n square h square epsilon naught by pi m z e square. So pi and pi are gone. So I'll get En is equal to minus z square e power 4 divided by 8 n square h square epsilon naught square. Are you guys able to understand this point? So again, when you substitute all the constants that are there in this problem, I'm sorry, in this expression, then you will get En is equal to minus 13.6 into z square divided by n square electron. At least this expression you guys remember? Right. So make a note of this. So those who are online, are you done copying it? Those who are online, are you done copying it?
Yes, sir.
Yes, sir.
Okay. Now listen. So based on this expression, we are going to have something like this. Okay. So this is how we derive the expression. What is it? From Bohr's theory, the energy of an electron, the nth orbit of hydrogen atom. So since they told hydrogen atom, actually the value of Z here should have been 1. Okay. It is 2 pi square mk square e power 4 divided by h square into 1 by n square. See, you need not remember this value. I already gave you the expression. Right. Now, according to the Bohr's frequency condition, whenever there is an electron. So what does Bohr's frequency condition tell you? Whenever there is an electron in higher orbit, it makes a transition to the lower orbit. Right. What is released? Energy is released in the form of what radiation? Paran. The form of radiations of discrete energy of photons. Means we have electromagnetic radiations coming out. Suppose this is the higher orbit. From a higher orbit, if the electron jumps to a lower orbit, then this is 2, this is 1. E2 minus E1 will be equal to H2. Are you able to understand this? No. The point is, Now, think of this logic. Okay. Now, think of this logic. E2 will be minus 13.6 into z square divided by n2 square. E1 will be how much? Minus 13.6 into z square divided by n1 square. So what is the value of E2 minus E1? Actually, I'll add a small correction. It is not E2 minus E1, En2 minus En1. Okay. So En2 minus En1, if I take, it will be minus 13.6 into z square if I take out common. It is 1 by n2 square minus 1 by n1 square. Am I right with this? So En2 minus En1 will be equal to minus 13.6 into, sorry, it become plus 13.6 into 1 by n1 square minus 1 by n2 square multiplied with z square. And remember, this whole thing is in terms of electron volt. So 1 electron volt, you will convert it to joule by multiplying with 1.6 into 10 power minus, correct, 10 power minus 19. So when you do all those things, listen to this. According to quantization condition, En2 minus En1, can I write it as Hnu? So Hnu is equal to 13.6 into 1.6 into 10 power minus 19 into 1 by n1 square minus 1 by n2 square into z square. Am I clear with this? Now, h into nu can be written as c by lambda. So hc by lambda is equal to 13.6 into 1.6 into 10 power minus 19 into 1 by n1 square minus 1 by n2 square into z square. Right. So from this, what can I say? 1 by lambda is equal to, that will be 13.6 into 1.6 into 10 power minus 19 divided by h into c multiplied with 1 by n1 square minus 1 by n2 square into z square. Accept it. Now, when you substitute the value of h and c here, when you substitute the value of h and c here, you will have 1 by lambda is equal to, listen to this, 1 by lambda is equal to capital R into 1 by n1 square minus 1 by n2 square into z square, where this capital R is called as Redbird Constant. You have heard this term? So you have this Redbird Constant, which is given by the value 1.097 into 10 power 7 meter inverse, and this formula is used to calculate the wave number. 1 by lambda is wave number. So to calculate the wave number when an electron transits between two different orbits. Okay. So based on this only, we are going to see a concept called as spectral lines of hydrogen atom. So what do you mean by spectral lines here? Observe. When an electron, right, when an electron makes a transition between higher orbit and the first orbit, I repeat, when a transition is made between the higher orbit and the first orbit, then the spectral series belongs to Lyman series. And according to Lyman series, the radiation that is getting released will have a wavelength which is corresponding to ultraviolet radiations. right? Here, the next is when an electron makes a transition between a higher orbit and it stops with the second orbit. I repeat, when it stops with the second orbit, then it corresponds to Balmer series. I dropped a message in a group player. Hello, online. You have mobile. Repeat travel. You didn't see the message. Next, okay. It's there online 6 o'clock Arabic. போயிட முடியுமா வீட்டுக்கு சீக்கிரம் okay, so if a transition happens between higher orbit and second orbit, it belongs to the Balmer series and the radiations fall in the visible region. Okay, third, Paschen series, when a transition takes place between the higher orbit and the third orbit. Call it as Paschen series. And fourth one, any idea? It's called bracket, and the last is fund. Everything. So I'm assuming you would have learned this thing at least. This is called emission spectrum. So read up. Finish. Okay. So this one, maybe you can make a note. So for any spectral series of hydrogen atoms, see, this is very, very, very rarely asked question. They'll ask you the frequency of H alpha line. So what do you mean by H alpha? If an orbit is the first orbit plus 1, and you call it as H alpha. For example, if I have Balmer series, at what orbit is the electron supposed to land for you to have Balmer series? Supposed to land at the second orbit. So what will be N2? So second is the first orbit according to Balmer. So for you to obtain H alpha line, an electron should make a transition between third orbit and the second orbit. Similarly, if you want H beta line, it should come from fourth to second. If you want H gamma, it should come from 5 to. So like this, it keeps on going. So when an electron makes a transition between the third and between the subsequent orbits, you call it as minimum frequency or maximum wavelength, or you call it as maximum wavelength. Okay. And N2 is equal to infinity is what we call it as the series limit, which has the maximum frequency. So sometimes how they will put the question is, the electron made a transition in such a way that maximum frequency is emitted. Then indirectly, what are they telling you? The orbit from which the electron is jumping is infinite orbit. So, or else they will ask you to they'll ask you to find an electron is making a transition between two orbits. Find the maximum frequency. Where will it happen? When the electron makes a transition from so next one is called as the energy level diagram for hydrogen atom. Okay. So what is this energy level diagram is basically, it shows you this diagram is basically represented in the form of parallel lines where each line represents, right? Each line represents the energy of that particular orbit. Sorry, energy of the electron in that particular orbit. It is a diagram in which the energies of the different stationary states of an atom are represented by parallel horizontal lines drawn according to some suitable energy scale. So this is 1, 2. Okay. So if I take the energy of the first orbit, so what is the energy of the nth orbit? It is minus 13.6 into z square divided by n square. If I take n is equal to 1 and z is equal to 1, z is equal to 1 is hydrogen. So when you substitute it, energy of the first orbit will be minus 13.6 electron volt. So this will be minus 13.6 electron volt. Suppose you want the energy of the second orbit, what will you get? You will get it as minus 13.6 into 1 by n square. You will get by 4. How much is it? Minus 3.4, right? Yes. So E2 will be equal to minus 3.4 electron. Similarly, if you want E3, what will you have? Minus 13.6 divided by, you will have 9 here. Because it is n square. So by 9, I would over. So you will have E3 is equal to minus 1.51 electron volt. Next, what will happen? E4 will be equal to minus 13.6 divided by 16. So it is 0.85. Are you able to understand this? It keeps on going like this. So this kind of a diagram, it's a set of parallel lines which represent the energy level of each orbit or electron in each orbit is what is called as energy level diagram for hydrogen. Am I clear with this? Yes or no? Done. Now see. So energy level diagram, this is what you're supposed to use. So this is how it looks like. So I already wrote the values -13. So it tells you the difference between the energy levels of different atoms. Here, if you see, the energy difference is slightly higher compared to other orbits. So as you go in the upward direction, when you travel towards infinity, the energy between the subsequent levels will keep decreasing. The distance will keep decreasing. Is it clear? And the last concept of this chapter is limitations of Bohr's theory. Okay. So the first point, by the way, those who are online, are you able to hear me?
Yes, sir.
Any doubt till here?
No, sir.
So limitations of Bohr's theory. This theory is applicable only to hydrogen-like single electron atoms and fails in the case of atoms which has more than 2 electrons. So here, what do I mean by hydrogen-like atom is, if I take for lithium, it will fail. What will I do? If I take for lithium, it will fail. But Li2 plus, it will pass. Why? Because it is not a hydrogen atom, but it is a hydrogen-like atom which has only 1 electron. Lithium level electrons, 3, out of which 2 are lost, means it will have 1 electron. So that is why they mentioned it. It is for hydrogen-like atom. It is not only for hydrogen. Okay. Similarly, in the spectrum of hydrogen, certain spectral lines are not single lines, but a group of close lines with slightly different frequency. So what is happening? When an electron makes a transition from a higher orbit to a lower orbit, you didn't get a sharp spectral line. Rather, you got a series of spectral lines which are slightly close to each other. And they also have slightly different frequency. Purida. Third. The third point is, so what is the shape of the orbit he mentioned? It's a circular orbit. But he never gave a reason why only circular orbit should be chosen when there is a possibility of elliptical orbits. Like how the planets revolve around the sun in an elliptical orbit, he never mentioned the fact that why it should not happen in an elliptical orbit also. But the thing is, if at all you propose an elliptical orbit, because in elliptical orbit also angular momentum is quantized. If you see from the gravitation concept, it is quantized. Okay. Only difference would have been in such a way that instead of having the center as a nucleus, you would have had one of the foci as a nucleus. So there was no explanation given. Okay.
Sir?
Tell me now.
Sir, in elliptical orbit, centripetal force won't be applicable, right?
Not necessarily. It's not about the centripetal force. That's
Sir,
what
in the sense, like, we can't equate it with centripetal force.
But here centripetal force has no role in the quantization conditions proposed by him. No? In the two conditions that he proposed, did he speak about centripetal force? He used it only in the derivation. He spoke about angular momentum and energy. Elliptical orbit, you can conserve the angular momentum. No?
Okay, sir.
Next one is, as electrons exhibit wave properties also, so orbits of electrons cannot be exactly defined as in Bohr's theory. So since what is happening according, so later it was discovered, right, that electrons exhibit wave properties as well. Means the electrons are not going to sharply have a circular motion, rather they will move in the form of a wave. Okay. And Bohr's theory does not tell anything about the relative intensities of the various spectral lines. So it predicts only the frequency of those spectral lines. Okay. And lastly, it does not explain the further splitting of spectral lines in magnetic field, which is called as Zeeman effect, or in electric field. So it does not explain the splitting of spectral lines in the presence of magnetic field, which is called as Zeeman effect, or electric field, which is called as Stark effect. Is the point clear? So these are all the drawbacks of Bohr's theory. Is this point clear? So if you, with this chapter is over. Right? So next few chapters that you have are nuclei. Nuclei also maximum 2 days. And semiconductors. So by next Tuesday, maximum you can expect the syllabus to get over. Is it clear? Those who are online, are you guys clear?
Yes, sir.
Maximum by Wednesday. I'm talking about physics, sir. Math will take time. Physics, I'm talking. Right? Yeah. So is there any other doubt? Is there any other doubt that you people have? So I'm assuming it is clear. Right? So the next class will start with the next chapter, that is nuclear. Okay, that is also an easy chapter. It is an extension of this chapter. Atoms and nuclei is actually treated like one chapter. Then you have semiconductors. Semiconductors also maximum they have deleted. So it is only till a concept called as rectifier, which will take 2 classes. Simple now. Okay. So in the meanwhile, keep preparing. I'll see you. Okay. We'll wind up, guys.
Thank you, sir.